Hey, it seemed appropriate to start this off by talking about this meetup that Angelo Saracino and I started in New York earlier this year, called New York Systems, that started popping up in cities around the US, India, and Germany. So it's especially, it's very special to me to be here and be a part of the DC Systems meetup starting up with all of you. So, who am I? I'm Phil. I've been a developer for 10 years. I started getting interested in databases 4 years ago. I was working on an inbox application that kept getting slower and slower as new items showed up in the inbox, and I had no idea what to do about this. So my coworker said, "Are you using an index?" And I said, "I have no idea what an index is." So I went home and built a little in-memory SQL database for myself that supported create, table, insert, and select. And when it processed the insert, it would build a little index, and when it processed the select, it would look for the index from the where clause and try to make use of it. So that was my first exposure to thinking about database internals at all, and I was completely hooked at both how accessible it actually turned out to be, and that there's so few people out there trying to explain this to people. So both of those were extremely compelling to me. And today I work for EDB on a distributed Postgres product. EDB is the largest contributor to Postgres, but I don't blame you if you don't know that. I'll put it that way. There are a number of folks in this room who are particularly experts on this topic, which makes it particularly nerve-wracking to be here talking. We've got folks who built FoundationDB, we've got folks who work on Coral, and many others who I'm sure I'm not addressing. You've also worked on some of the systems that I'm covering, so yeah, bear with me. The point of this talk is primarily about fundamentals and behavior of distributed consensus. It's pretty relevant, I think, for any backend developer today, because almost all of the infrastructure that we use, for example, Kubernetes or Elasticsearch, is actually built on distributed consensus. So even if you're not going to go home and build Raft, which honestly I encourage you to do, I hope you'll still take something that's pretty relevant to your job. And this is also the first talk that I have given in a long time, so again, let's go. All right, so you've got an application, and you've got some data. And the data is on a single node, which makes communication between your application and the database very simple. You can write to the database, and you read back data, and you get exactly what you wrote. For example, in a timeline view of it, you might set some key to some value, and eventually the database will respond. We'll say OK. And when you go to read that key back, you get back the value that you expected. There's nothing shocking here, but this term, the term for this is called consistency. And it is a spectrum of behaviors, where to be completely consistent is a term called linearizable. And it's most easy to think about linearizability by thinking about what's not linearizable. So back in this timeline view, for example, when we set a key to a value, and we get the response back, and the database says, OK, that write was successful. But then when we try to get back that value by key, the database does not give us back that value, even though it said the write succeeded. And maybe in the future, we make that same request again, and this time it gives back the value that we expected. So this is a counterexample of a system that is not linearizable because we got a stale value back. It said that the write succeeded, but when we went to read it, it did not give us back what it said we wrote. This is just one example of being not linearizable. We can find a more formal definition on the Jepson website by Kyle Kingsbury. I will not read many quotes in this, but I will read this one. Linearizability is one of the strongest single object consistency models and implies that every operation appears to take place atomically in some order consistent with the real-time ordering of those operations. I bold single object in this because when programmers thinking about databases hear the word consistency, you might think about the consistency in ACID. And this is not that. ACID and transactions are about multiple objects being consistent or not. Linearizability is much simpler. It's just for a single object, is it consistent or not? And when we're thinking about a single node, especially a single threaded node, this is not very interesting. If you have an in-memory hash table and you update a value in that hash table and you try to read it back, you expect to get back exactly what you just wrote. That's not shocking. But if we consider this as a property in general, it's actually really interesting and useful because there can be systems that are linearizable even if there were not actually a single node. And this is particularly important because if a single node database crashes, you can no longer read or write at all. So the first intuition, the zeroth intuition that I would take away from this is that a single node is not highly available. It's not particularly. It is particularly obvious. But that leads us to how do we achieve high availability? And at some level, it seems pretty obvious we can add nodes. And if one node crashing meant that the entire system became unavailable, presumably we can add 2 more and then somehow we'll be able to keep reading and writing. But the question then becomes where you read and write from. If you send writes to all 3 of those databases, and one of the databases goes down and eventually comes back up, what does it do about any writes that it missed? So how do you keep the data in sync? One of the most common tools that programmers reach for is read replicas, where you have your application and it will primarily interact with a single leader, and that leader will handle replicating to replicas. This is great and simple, but on the leader failure, if you switch to one of the read replicas, there's no guarantee that what you wrote to the leader is actually on the read replica, or in general, this is how read replicas work. So this system is not linearizable and violates the property of simple squareness. So there are a bunch of options for achieving linearizability and high availability. Many of these are obscure, but I'll just explore them anyway. Chain replication is one used often by file storage systems such as EBS. Kafka has their own replication protocol. FoundationDB has their own replication protocol. Blackside forms are another one you can read about. And the last one is distributed consensus. Again, this is not a complete list, this is just a couple of the popular options. If you want to read more about all these different options, Alex Miller, who happens to have worked on FoundationDB, wrote this really great blog post a month or 2 ago that covers all of, or not all of these, but many of the design decisions chosen by people when they pick these different methods for consistent replication. I really encourage you to read this, it's a really great post. But the most popular method for consistent replication for high availability, and one that we're going to talk about, is distributed consensus. So again, this is a method for us to achieve linearizability while being highly available. And examples you've probably heard of, Raft, and some lesser known but still commonly used ones are multi-task system these types of replication. As I said in the beginning, these are used everywhere. In Kubernetes, Elasticsearch, Mongo, Cockroach, Tyreal, the product that I work on, and a bunch more. And we're going to focus specifically, though, on Raft, because it happens to be the most popular one. It's the one that you're going to come across most often. So at a high level, a Raft cluster running Raft software there will be multiple nodes that form a cluster that all talk to each other. And they'll decide among each other to elect one of them as a leader by majority vote. And if at any point in time the leader becomes unavailable, the cluster will elect a new leader. And your application will talk with whoever the current leader is. And they'll send commands to the leader and ask the leader to replicate these commands. So you will model your data as a series of commands such as this one set. You'll ask the cluster to replicate and execute this set command. And then maybe in the future, you'll ask it to replicate and execute this get command. Weird place to put this, but yes, when leader election is happening, as we just talked about before, you can't do any of this log replication. The leader will take each of these commands to client set and store them in a log in order that it receives them. So first we ran that set command against the cluster, and then we ran the get command, and that's how the leader stores these as a history in a log. And the leader handles replicating that to all the other nodes in the cluster in order. So for example, this is a log view of those three nodes in the cluster, where the leader is on the left, the k store B is in the middle, and k store C is on the right. The leader has a set command in the index number 1. K store B and C have also replicated that set command. K store A has replicated this get command that we showed. K store B has not gotten it yet. That might be because it is no longer able to communicate with the leader, or it might be because it just has not completed writing that log to disk yet. But K store C does have that entry. And then finally, at the very bottom, we see an entry that only the leader has that has not been successfully replicated to the other two nodes in the cluster. And the way that graph works is that once the majority of nodes in the cluster replicate a particular log entry, that entry is considered committed. And you can also think of committed as being durable. So in that example, by color-coded, the blue is what has been committed by the entire cluster. Green is what has been replicated. Red is what has not been replicated. And log index 2 has been considered committed by the cluster on the whole, even though K store B is not aware of it, because the majority has replicated this up to this index. Once a entry has been committed by the cluster, each node will apply that committed entry to a state machine, and the leader will return a result of that state machine to the client. So that is all very abstract, but if we wanted to build a distributed key value store on top of the graph, what that means is that we have to supply this state machine that might look like this to the Raft cluster. The Raft cluster itself will see each command as an opaque array of bytes. It's up to us and our state machine to interpret those as something meaningful. So since we're trying to model a key value store, we will try to parse those arrays of bytes for each command and consider them to be a set command or a get command. And we'll update an in-memory state for a set command, and we'll read from an in-memory state in a get command. Right. In a real environment, you will not put reads like I did into this log, because there are many ways that you can handle reads consistently without replicating them, but I wanted to show, for the sake of the state machine, that you might have multiple different types of commands that you want to interpret in the state machine. So the first major intuition to take away from here is that consensus is doing more work than if you were going to do this with a single node. In a single node database, when we want to write some data, we just write it. But in consensus, we have to replicate that write command to all the nodes in the cluster. We have to wait for the majority of them to respond, and then we can apply that change locally to our state machine, and then we can return. So consensus, in other words, means higher latency, lower throughput than if you were just doing reads and writes in a single node. One of the nice properties of distributed consensus, though, is that it can be easily put into libraries. These are a bunch of them. I don't particularly recommend you looking at these for learning the system, but these are good production libraries. A couple of years ago, I wrote a blog post walking through how you might implement this yourself. So if that is interesting to you, then feel free to read that. And it also has a number of resources in this post. Because as I said in the beginning, I do actually encourage you to go home and implement around, but I do not expect that everyone will. So the thing to remember again is that although we can encapsulate this into a mass library, the state machine is always specific to your application. That's why I had to show you that code where for our key value store, we implemented parsing command saying this is a get command or this is a set command. So now that we've talked about the basics, how are people using it? There are two major ways that people use this that I'm going to talk about. I'm not saying these are the only ways. In the first method, we use consensus both for managing who is in the cluster membership, and we also use consensus to manage what is replicated, the data. An example of this is this product called RQLite. This puts SQLite underneath or on top of Raft. So you send a SQLite statement like create table, and it replicates that create table string. And once it's been replicated by a majority of nodes in the cluster, it takes that create table and runs it against a local SQLite database. So this is a way that all the nodes in the cluster will have their own copy of the SQLite database, but it will stay completely in sync with all the other nodes, or at least the majority of them. This is one approach to using consensus to solving a problem. But that is a little bit niche, even though that is used in production. More commonly, you'll do what databases like Cockroach or Tiger like CP do, and you will have each key value or each row be an element in that log. In addition to doing cluster management, like every time you do an insert in a row, that row itself will go into the consensus log. And then there's an entirely separate set of databases where they'll use consensus to manage who is considered to be in the cluster, and maybe even who is the leader of the cluster, but they'll replicate the data plane separately, and no rows would go into the consensus at all. An example of this is chain replication, as mentioned in the beginning, which is what EBS uses, and Delta, which is another storage product by Meta. And similarly to the product that I work on also, we use consensus to manage who is considered to be in the cluster, but that is not how we replicate rows. This is another blog post if you're interested in seeing how you might model something like Postgres on top of distributed consensus. Yeah. So this got really far, and we talked for a while, but why, again, are we doing this? We started down this road because we wanted availability. And when we talk about availability, we have to talk about faults, which are a fancy term for any reason that a service might become unavailable. It might be because a process crashed. It might be because you can't talk to other nodes in the cluster. And it might even be that nothing is particularly wrong, you're just going really slowly. All of these are what might cause a fault. And Raft has a particular property, and distributed consensus in general tend to have these properties where if you want to handle some number f failures, you're going to have to set up a cluster with 2f plus 1 nodes. This is a particular property of Raft. So for example, if you have a 3-node cluster, you're going to be able to handle 1 failure. So if a single node goes down, you can continue to make progress, you can continue to replicate, you can continue to elect a leader. But if a second node goes down in a 3-node cluster, you can't. Similarly, for a 5-node cluster, you can handle 2 failures. And if we went to an absolute extreme, 101-node cluster, you'd be able to handle 50 failures, which sounds super fancy. But how does this behave in different environments? So imagine that your processes are constantly crashing. For example, you have some bug, and just every time it starts up, it just goes down. Or maybe you're being killed by the boom killer. Or maybe disks are really slow, and you send a write, and it just takes forever to complete. So you can't, and you're synchronous, you have to wait for these logs to be committed to disk, but you can't because the disk is so slow. And similarly, if the network is very slow, or if the network is just completely unavailable. In these situations, it's going to take you longer to achieve consensus. It's going to take longer to replicate the log. Elections are going to happen more often, and when they happen, they're going to take longer to succeed. And again, the bonus point here is that when the later elections are happening and they take longer to succeed, they also block replication. So for clients, that means in these worst case environments, you're going to get worse throughput and worse latency. So Tiger Beetle built this really cool visualization at sim.tigerbeetle.com. I'm not going to play this for you, but just tell you about it, and you can go over this when you'd like to. They implemented vstamp replication, which is a similar consensus algorithm to Raft, and they swapped out the I/O layer so that they could inject faults. Faults for them meant things like process of crashing. So nodes in the cluster. Each of these 5 bugs is a node in a 5-node cluster. They also injected latency in the network and on disk. And they showed this across different levels that got progressively worse. And they showed you visually that it was taking longer for the log to get replicated, and that leader election was happening more frequently, and that, again, when the leader election did happen, it took longer to complete. So, yeah, I highly encourage you to go watch this if this is interesting. In contrast, if the processes are stable and they're not crashing, and your disks are fast, and the network is fast and reliable, the leader is going to get elected quickly, it's going to be stable, it's not going to have to change who is the leader, and logs will get replicated quickly. Which means for clients of the system, this is the best case for throughput and latency. So the next major iteration takeaway is that throughput and latency will deteriorate as the environment worsens. what about something completely different? I already brought up the crazy scenario of a 101 node cluster. So what happens in that kind of situation? We started talking about consensus because we wanted availability with consistency. And if we want extreme availability, we could just add more nodes, right? Because again, for a 5 node cluster, we'll only be able to tolerate 2 faults. And for a 101 node cluster, we're going to be able to tolerate 50. Which sounds super highly available, and it is. But the communication is its own penalty in this situation. If you've got a 5 node cluster, the leader needs to make 4 requests for every log entry. It will count for 1 request on its own. It doesn't need to make a request to itself. And it needs to wait for a majority, so itself plus 2 other responses, before it can consider a log entry to be committed. And then in contrast, if you consider this 101 node cluster, the leader is going to need to make 100 requests for every log entry, and it's going to need to wait for 50 responses before considering that log entry to be committed. And this is starting to come up against a general principle of services in general, which is that we're going to get slowest sub-request. There's a great visualization of this in Designing Data-Intensive Applications, the first chapter by Martin Buckman, where you've got this web application, and even though it can make these 7 requests in parallel, it's going to be bounded by the slowest one. And in a quorum system like Raft, it's not so bad. We're not bounded by the absolute slowest one because we only need a majority of nodes to respond, but we're still bounded by how slow the fastest majority is. And this is before we even consider tail latency, which is a fancy term for variability. There is this popular table by Jeff Dean, and Simon Skilson has another one, that are guidelines for latency of a bunch of different operations. But it is also pretty misleading because it doesn't really help me that much to know some like single guideline, because all of these are not, it's not really meaningful to know a single one because every latency is a distribution. And these tables don't show you that. So for example, with the network, Evan Jones also got annoyed at these tables and did his own study of connection latency in localhost and in the same zone and across zones, and published this. And I'm just showing that there is a distribution of latencies here. And similarly, for disk, Jens Expo has this utility called FIO that you can run on your laptop, and you decide to run it with IOU ring or just synchronous IO, and it will run read and write workloads for you, and all I've highlighted here is this distribution of latencies. So the point with this distribution is that as you have more requests going on, you're going to become less predictable. And this leads to the third major intuition, which is that throughput and latency deteriorate as the size of the cluster grows. So if we couldn't add nodes to scale, we added nodes because we wanted more availability, that makes sense, but like normally you think scale, you think add more nodes, but we showed that that is not going to work. So how do people do it? Some databases that are able to horizontally scale will shard the data. Examples of this, Cockroach, Gigabyte, TIDD. And they will use consensus, but they will use consensus to replicate within each shard. And at the same time, just know that many databases do not shard. For example, etcd or console, there's just a single consensus for the entire space. There's no horizontal scale. There's no benefit, there's limited benefit of adding additional nodes, and you will incur the throughput and latency costs as you add this.
I was going to say there's one cool side effect at the top when you shard on top of consensus is you get multiple leaders. Because with base, raft, or paxos, to get linearizable reads, you can only read from the leader. But if you shard, you can distribute leaders around your cluster. That's just fun.
I also don't want to talk about two-phase commitment. So if we look at the Cockroach, you might have a 5 node cluster like this that's all running Cockroach. And the way that they do it is they map your SQL rows to key value, to a key value store, and they shard the key range. So for example, on the left, hopefully you can see that. On the left, for range 0 to 9, 3 of these nodes will store data in the 0 to 9 key range. And it is still replicated, but not every single node has all the data. So that's part of how they horizontal weighting scale. Yeah, right. So this kind of gets into an issue that I have when I see any database say that they're distributed. Horizontal scaling means sharding. Does distributed mean sharding? Not necessarily, because we're talking about distributed consensus, and we said that we haven't seen it yet. Does consensus mean sharding? Definitely not. So the fourth big takeaway is that distributed consensus has nothing to do with horizontal scaling. And just recapping, 0th point, single node is not highly available. Consensus, as I said, think back to the example, if you want to process a write, when you're doing consensus, the leader has to take the write, replicate it to all nodes in the cluster, wait for majority, and then only once the majority has replicated it can it go and process. So it's not free. The latency and throughput of consensus will get worse as the environment worsens. For example, if more processes are crashing, or if the network is down, or if disks are slow. The latency and throughput will also get worse as you add nodes to the cluster. And again, distributed consensus has nothing to do with horizontal scaling. This talk is an adaptation of a blog post that I wrote a couple of months ago that got input from a number of folks online, and if you are interested in following distributed systems people on Twitter, I highly recommend these 5. And that's it. Thank you.